Okay, I guess probably more colleagues will join, but I suggest let's start with the introduction and let's get going to hear about about two interesting 5G-ACIA endorsed testbeds today. First, I'd like to introduce myself. My name is Lisa Underberg. I'm with the Institute for Automation and Communication, and I'm also chair of 5G-ACIA's working group 5 with the name Industrial 5G in Practice. And that's what we are going to look at today with two of our testbeds at Industrial 5G in Practice. The first testbed will be covering Open RAN technologies, and the second one will shed a light on mmWave operation. But before we get into the technical details, I'd like to give you some quick housekeeping information on how we are going to conduct our web seminar today. So we will have these two presentations. They will be held back to back with no questions in between. We will have a joint Q&A session after both presentations. But that you don't forget your questions, feel free to use the Q&A window anytime during the presentation. We will go back to the Q&A window in the end of the presentation and hear what our speakers are answering to your questions. So write your question as soon as it appears. We will try to address as many questions as possible in the end of the web seminar. But if questions remain open, of course, you can become a member and get more information in general about 5G in industrial applications, or you can get in touch also with our 5G-ACIA office. This web seminar will be recorded, and the recorded version will be available afterwards. This is why everybody except for the speakers is muted by default, which is why you need to put your questions to the Q&A window. And I, as the moderator, I will ask them then later to our speakers. If you have any technical problems, please feel free to use the chat window or reach out to 5G-ACIA office via the given email address here. Fabian is joining here for technical help and is eager to answer your questions. There will be a couple of live polls, mainly in the beginning, and the polls will be popping up, and we would like to get your feedback just to get to know your opinion and your background a bit more. So to practice that, let's start with the first live poll. And I think Fabian is from the office is supporting that and asking which stakeholder group you belong to. Now, for me at least, there's a pop-up window, and now I can click my stakeholder group, and I think in the chat window or in your pop-up, you will see the live results. So we'd be happy if you took some seconds to fill out your stakeholder group. I think that looks well balanced. ICT and OT almost the same proportion, and then we have some academia and some others. That's pretty nice, as 5G in industrial applications indeed is a topic to all to ICT and OT, as well as to academia. Okay, 21 answers. I'd say let's go on to the next question. Which region do you come from? There will be options targeting continents, and looking at the time, I would expect we have Europeans here, maybe someone from Asia joining late, and probably from the Americas. Let's see if I'm right. Oh yeah, Europe is. Most people are from Europe here, but some Asia. So good night, good afternoon, late afternoon to Asia, good afternoon to the European colleagues, and good morning to North America. Thanks everyone for joining. So after we practice that, and we have already passed some time, let's get to the first presentation. The first presentation will be given by Ralf. He's with Fraunhofer IIS, and he will report from the testbed that was working with 5G Open RAN technologies. And Ralf is going to share his screen. And I guess that works now. It's coming up, Ralf. The stage is yours.
Perfect. Thank you, Lisa. So, hello, everybody. I'm working at Fraunhofer IIS in Nuremberg and Erlangen, and I'm dealing with 3 different 5G testbeds. And today, I'm going to speak about one of these testbeds. It's the biggest one that we actually run. A bit of background. Back in 2019, the Bavarian government funded a project called 5G Bavaria. The goal of the project was generally to bring the 5G technology, the new 5G private network technology, to the companies. It was a new technology, and Bavarian government thought it is worth to force it a bit and to push this technology and pave the way for the technology. So they asked us as a partner to build up an open 5G campus test network that would be accessible to especially small and mid-sized companies, where they could talk to us about 5G and get hands-on experience. Going back 2019, 5G standalone campus networks were not at all, let's say, common. It was the beginning of this new technology. We started to think about the project. We already applied for a license, for a private license, 100 megahertz in Germany. You get it in the N78 band. And so we digged into the topic and quickly found out that there's a new interesting technology available that is Open RAN. In my past experience, I worked a lot with Ericsson networks and with other commercial networks. They are excellent technologies, but they have one major drawback for the end user. You can't access the inside of the network. You can't change parameters freely. You can't take traces as you want. And especially for us as a research institute, it was very important, and we decided quite early that we go for Open RAN, because this will, let's say, open up the black box for us. We can change parameters and we can take information out, meaning we take traces. On top of that, the Open RAN technology came with complete, let's say, system virtualization and cloudification. So all the system components, the DU, the CU, even the core, they run in virtualized environments in a container, and you can put them just on any commercial off-the-shelf hardware that you want. And this also gave us a lot of new opportunities to work with the campus cloud, to work with Edge at our 5G network. Finally, we thought that Open RAN is a complete new emerging market, and we thought that Open RAN will, let's say, be a game changer for this industry. It will open up the market by creating competition and competitive prices. That was our idea, to go with Open RAN. We then, let's say, quickly realized that this new technology is pretty much complex and it's not, let's say, that advanced. So we decided to go with a partner that has some experience with a system integrator. In parallel, we analyzed the market a bit, and we found at this time, as I said, it is 2019, we found Airspan as an Open RAN supplier, and we found Metaswitch as a core supplier, as, let's say, quite promising technical partners, technology partners. So we decided to go with them using a system integrator in the middle. Together with the system integrator, complete radio planning was done with an external partner. This is something that really pays off. Take someone that has experience with all this radio stuff to define exactly the places where you put the RUs on, to check the coverage areas, and to give a prediction where you have good coverage, excellent coverage, and where you have the edge of the coverage. It then took a lot of time, I have to say, to do the just practical work, like installing the fiber cables, the power cables, and the mounting points for the complete network. We speak about roughly 30 radio units. We see this a bit later. So it was quite some time that was used just to do all this basic stuff. Yeah. And then also we decided not to do the complete installation of the 30 units in one step, but to do a stepwise approach. start with a small initial setup, get first experience, and then maybe even change the planning of the other parts of the network a bit based on on this first experience. Also, we are in a lucky situation that in Erlangen and in Nuremberg, we do not have any neighbors in our industry areas where we are that also run 5G campus networks. So any interference problems or any interactions with neighbors regarding aligning frequencies, slots, formats, whatever, did never come up to us. So still today we can operate complete independently and we don't disturb anyone and we are not disturbed by anyone. Another topic that we did in this time is that we did all the legal work. So for every station that you mount and that you switch on, you need to get Standortbescheinigung from the German regulator, the BNetzA, just to be on the safe side and that everything is okay. We then started 21 with the real installation of the system and figured out quickly that even 2021, we were still quite early adapters of the Open RAN technology. So there was not a widespread, let's say, base of reference systems or even test systems. At this time, I think only 150 licenses for private 5G campus networks have been issued by this Bundesnetzagentur. So it's not a lot. And from these 150, at least half of them was like research institutes, universities. So not real commercial used networks. When we built up the stuff, we found a lot of issues. I don't want to dig into them and don't get it wrong. This is not a blaming of any special vendor. I mean, every vendor has its own issues. We just had these issues. We had a lot of synchronization issues between RU, DU, and the CUs. It took a lot of time to get the time sync protocols, let's say, running stable. The complete stability of the system back in 21, it was not sufficient. Then, as you have a RAN from one vendor and a core from another vendor, you have two different management systems, which makes it again quite complex because you have to handle 2 times the complete system setup. And for your KPI analysis, for example, you also have to gather data from 2 different systems with different formats. So it's simply not really convenient. The next thing back in 2021 was that configuration changes were barely possible. So you could maybe change the power, but that was it. Changing MIMO configs on the fly, let's say, or changing uplink, downlink slot formats, it was simply not possible. And even today, you don't find this very commonly spread. Another issue that caused a lot of problems was the virtualization topic, because there you are in the middle of the IT domain. So you work a lot with OS level problems on Linux kernels, on things like that. You work with all these virtualization management tools, Ranger, etc. So it just takes some time to get into it. And I have to say, even today, this complete complex is not an off-the-shelf working solution. It still takes quite some handwork. Another big topic back in 21 was the UE interoperability. It was at the beginning very poor. Many UEs, CPEs or smartphones, whatever, they simply didn't work with private networks due to a special network numbering scheme that is the mobile country code of 999. And this country code was barely accepted by user equipments at this time. It changed a bit, but still this is an open topic even today. Software upgrades. I mean, at this time, a lot of software upgrades came in. All the suppliers worked on their systems, and the software update process, due to the complex setup with virtualization, with Linux, special Linux kernel versions, etc. I mean, this was also quite complex. And finally, even today, it's very hard to find eSIM support, but back at this time, eSIM support was not at all available in the domain of Open RAN private campus networks. Based on all this experience, and also by the fact that, for example, the Metaswitch core was bought by Microsoft and it was transferred from an on-premise solution to a cloud-based solution, which we didn't want, we decided to change the network setup a bit, split the network basically, and take another supplier in. At this time, end 21 up to mid 22, it became obvious that different suppliers had different roadmaps, and one roadmap fits more the use case you want to do here, and another supplier has other features that you use in different projects, for example. So we decided to go with 2 vendors in the future, and we replaced part of the Airspan network with a QCT network. QCT was an upcoming Taiwanese manufacturer. It's basically the same system approach. It's an open RAN approach running on COTS hardware. But we decided to split the network. I will show the setup of the network in a second. Also, when we talked about first customers and we did first customer projects, we found out that Wi-Fi 6 is a very important topic, and many companies have the issue. They want to do simple comparison between Wi-Fi 6E, for example, performance, and 5G-ACIA performance. So we installed a complete Wi-Fi 6E network as well for comparison reasons. Just to give an overview, I will not go too deep into this. On the right side, you see the site of Erlangen. At the site of Erlangen, we have some airspan nodes, and we have a big antenna mast, 40 meters. This complete setup is only used for internal research projects. Then you have the site Nuremberg. In the site Nuremberg, you have the complete core systems for QCT and for the change to Druid core now. As I said, we moved out the Metaswitch core and replaced it here with a Druid core. Down on the bottom, you see our industry hall. This is the test hall where we run the industry projects. And there you see that we have 8 QCT radios. The hall is 1,200 square meters, and we have 8 units in there. I come to this in a minute. As you can see here, the complete network is split up in 8 G nodes. It goes with 30 RUs, and then we have some Wi-Fi 6 equipment. And this is all in an indoor and outdoor area. So we have in Nuremberg, in the customer area, so to say, we have also an outdoor area near the test hall where we enable our customers. You see here, this is the industrial indoor hall, and this is the outdoor area. This is also covered with a QCT network. The office area is covered with an airspan network and is only used for internal research projects. Below here, this is a look into our test hall that can be customized for industrial use cases and industrial customer projects. And we have the outdoor area, so we can do indoor-outdoor transitions, even with heavy trucks go in and out. Regarding the performance, I will not spend too much time here, but what we found out is performance increased a lot over time. What we see today, Airspan, for example, only supports, at least with the revisions, the hardware revisions we have, only supports MIMO 2x2, which gives us then 550 in downlink and 60 in uplink. QCT, for example, they support MIMO 4x4, which gives us a stable 1 gigabit in downlink and 460 in uplink using different coding schemes. The good thing with QCT is they already today offer a split, let's say a change of uplink downlink slot format. So you can change between a downlink heavy slot format, you can do a symmetric slot format or an uplink heavy slot format. Of course, this 1 gigabit in downlink is done with a downlink heavy slot format, and the 460 in uplink is done with an uplink heavy slot format. Regarding the latencies, I mean, it's fair to say that we are about 20 milliseconds. You can discuss about 19, sometimes 17, 21, but 20 milliseconds end to end. This is what we, let's say, currently reach in our network as a stable status. I will just show some pictures, only as an impression. It's just some radios that are mounted, some more radios that are mounted. And there we see the pictures of the installed IT systems. So basically, these are all the cores, the CUs, the DUs of the two networks, the Airspan Druid network and the QCT network, as they are split across the building areas. But what you see here is basically the complete needed infrastructure to operate 30 radio units in-house. To maintain and check not only the network, but also support customers, we do have a quite mighty setup of measurement equipment. So we have a 5G protocol analyzer. We have the from Rohde and Schwarz, we have a Romes and Qualipoc test solution available, spectrum analyzers, and we have a transport network field tester from Viavi, which is very important to find problems in the time synchronization domain of your network. Regarding the UEs, it's fair to say that the situation has improved a lot. So especially industry-grade routers, they tend to work quite good in 5G standalone campus networks. Also, we have to say that most of these routers, they are based on 2 or 3 modem versions, and they are built into these small communication cards, as you can see them up here, like this one from Quectel. So it's only a small number of really chipsets and modems that is then spread to a large number of routers, but they tend to work quite good. Different phones, tablets, they also tend to work quite good in this network. But in general, the blacklisting of private networks in some devices, high-end smartphones, whatever, with this special MCC number, it is still an issue. And as you can see, 18 out of 28 that we have in our lab, they work without problems. This is the status of October, so maybe 1 or 2 have improved due to a newer software version. But still, it's not 100% sure that the device that you want to bring in does really work in your network. The current status of Open RAN now after 3 years is the stability gets close to industry grade. So it will take, I don't know, half a year, maybe 1 year, and then we will see the first Open RAN based systems out in the industry with 0.99999% availability and really good performance. Also, we see release 15 is missing a lot of things that the customer demands, especially low latency, but also positioning, for example, is a native 5G feature that comes with release 16 in the first version. It's urgently asked by the customers. So I don't think we will see a lot of commercial release 15 networks. I think the big shot will come with release 16 with, as I said, especially low latency features for industry and also positioning. What is still missing in Open RAN is still a broad base of installed systems. So we still don't have more than like 300 systems installed in Germany. And many customers say, is my use case already covered in one of the installations out there? And then you say, no, your use case is not covered yet. So you will be the first one. And then some of the interested people, they just withdraw because they say, no, I don't want to be the first one. It's not me. But still, we believe in the Open RAN approach, and we're going to follow this for the next 2 years at least. And we even want to expand with more vendors in our network just to broaden the scope that we can offer. Just a very quick, the performance in general has improved a lot over time. We are away from industry grade, but we are close to get it. What is fair to say, there are all-in-one G nodes. All-in-one G nodes and small cells, they bring, so to say, the CU, the DU, and the RU in one small box based on a special chipset. They are working very stable and quite good. The complete setup is much more stable than the vRAN approach. As I said earlier, 5G, it is a hot topic in the industry. Many people are interested, but in 1 or 2 years. That is basically the main message that we get, at least. Yes, we are following this topic, but it's too uncertain. It's a bit expensive, maybe. It's maybe not that battle-proven as it should be. So I hope that we see a much more rollout of Open RAN-based campus networks in the industry in 1 to 2 years. Based on this experience, we have created an interesting measurement, influence of traffic pattern white paper. It sets the relation between latency change due to mobility and handover topics. This paper is available on demand after the Hanover Mess, or let's say to the Hanover Mess. Finally, I just want to thank the 5G-ACIA. They hosted us now for almost 3 years as an endorsed testbed. We gave this endorsement now back, but we're going to reissue our testbed as a new 5G-ACIA testbed with a slightly changed scope. So we're going to focus more on positioning topics rather than communication topics, because we see positioning as one of the killer features for 5G in the industry. Looking at the time, Lisa, I think I will stop here.
Perfect time management, Ralph. Thank you very much.
Thank you
for your presentation. Without further ado, let's move on to Niklas and Bart. They will share their screen now. Niklas is with Fraunhofer IPT, located in Aachen, and Bart is with Ericsson. We see your PowerPoint editing view. Maybe you need to change that. But I will use the time to remind everyone, if you have questions, please feel free to write them right away in the Q&A window or in the chat, and we will address them after Bart and Niklas finish their presentation. And now we see it in presentation mode. Niklas, Bart, the stage is yours.
Okay. Good afternoon, everybody, and thanks for joining also from our side. First of all, maybe is the voice quality sufficient?
Yeah, I guess it works.
It works. Okay. Yeah. My name is Niklas Beckmann. I'm from the IPT. My colleague Bart Mellatz from Ericsson will take the second part, and then we will also present you a little mmWave demo in the end. Okay, what are we going to talk about today? We are going to talk about general mmWave for industrial applications with high bandwidth demands. We will give the example of our mmWave network, and as I said, we will finish with a small demo. Let's first start with a question. What's the motivation for becoming a 5G-ACIA mmWave testbed members? I know that mmWaves is a quite much discussed topic. We have lots of advantages, but also, of course, some drawbacks. One main advantage that I would say is generally that the under 6 gigahertz frequencies are mostly occupied, and it's not possible to get a bandwidth of 800 megahertz in total there. This will be enabled due to mmWaves. Yeah, we all know the Shannon theorem, and we know that high bandwidth is an enabler for higher data rates, and therefore also lower latencies. Yeah, easier interference management is due to the beamforming principle that can be very well applied in the mmWave domain. We have a spatial division of the different mmWave beams, and therefore the beams do not interfere even if they are in the same time slots or the same frequency domains if they are pointed towards different directions. Yeah, let's also talk about the drawbacks of the mmWave spectrum. Having a look at the free space path loss formula, for example, we see that with an increasing frequency, also the attenuation increases for electromagnetic waves, and therefore, obviously, the attenuation in the mmWave domain is much higher than in the sub-6 spectrum. We use the beamforming principle to add some gain to the mmWaves and to yeah, to find a solution for this higher bandwidth, for this higher attenuation. But also good beam management is important there. And then a simple practical drawback, which will be hopefully solved in a few years. There's a lack of available industrial 5G devices at the moment. Yeah, what are let's quickly look at the aims of the testbed. My colleague Bart will tell you more in a second, but we want to research on the performance characteristics, on the propagation and the network quality at the millimeter wave spectrum. Here, especially in an industrial environment, we want to see what influence radio configurations can have on the performance. And we want also to test the 5G UE, the user equipment configurations on the performance. We are able to configure different uplink or downlink TDD patterns here. And yeah, also we basically want to evaluate if millimeter waves are robust enough for the industrial context. Let's quickly talk about the testbed itself. On this slide, you can see the testbed members. Here we are at the Fraunhofer IPT. I already mentioned that. My colleague Bart from Ericsson is also here, but other partners are Qualcomm, Basler, and Rode und Schwarz. And the testbed lifetime until now is planned until September 25. Yeah, we are here at the 5G Industry Campus Europe, which is another 5G-ACIA testbed. We had also one of these 5G-ACIA webinars, I think 2 or 3 weeks ago. And this testbed is integrated in the other one. What spectrum are we using? We are using the N258 band, which is between 26.7 and 27.5 gigahertz. We have the before mentioned 800 megahertz there. In the frequency range 1, we have the N78 band, which is typically reserved for industrial use cases. And then we have the LTE anchor bands. Yeah, our facility, you will see a little bit of our facility in a second when we start with the live demo. But we have 2,700 square meters here. Here in this production hall, we have roughly 50 machine tools. And one of them you will see in a second. Yeah, here you can see pictures of the millimeter wave cell. The millimeter wave antenna is deployed here at the IPT shop floor aisle, and the use case that we will present in after Bart's part will be the data stream in a multi-tool cell. Here you see another picture of the size of our shop floor. So you see we have many machines here. And with that, I will give the presentation to my colleague Bart.
But then also welcome from my side. My name is Bart Millers from Ericsson, and we are essentially neighbors to the Fraunhofer IPT here in Aachen. I want to introduce a bit the testbed approach that we have. We have a kind of phased approach to our testbed setup. Of course, before we can start working, we have to set up the testbeds. Then a second chunk of activities that we are planning and have already started is executing measurements within the range of what Niklas has also been hinting at. And then a third chunk of work is going to be the use case implementation, where we want to explore what benefits and drawbacks millimeter wave can have to realize use cases in the industrial setting. If you now look a bit in more detail the different phases, setting up the testbed. Of course, in order to have millimeter wave available, we need to install and configure the radio equipment. You see the same picture here in the middle of the screen. where we have a millimeter wave antenna, and it is accompanied by an LTE band. I'll come to that in a second. You see a bunch of different millimeter wave UEs, or if I can call them UEs. It's not really yet industrial equipment. I think that is a bit in line with what Ralph was saying earlier. The device availability for industry is still rather low compared to the consumer market. And here for the millimeter wave area, it's still, we're still starting up the devices. So there's still a lot of evaluation type of devices that we're working with. Since we're talking devices, the reason here for the band 7 or the LTE antenna, which is in band 7, was actually one of these things that you also find out while you're integrating devices is, even if you look at data sheets, you will see that individual bands like N258 and band 7, band 40 in LTE are supported. Yet you have to find out the hardware sometimes that the band combination is not supported. And that is what's caused us then to go for a secondary LTE anchor in our ENDC deployment that we started with. All in all, the device integration has been for quite a while, and whenever we get our hands on new devices, we of course integrate those into the millimeter wave cell. What we have now recently done is also install a second so a second millimeter wave antenna in the same facilities that Niklas was showing earlier, for which we can then use to experiment with different TDD patterns. It will explore things like the interference of 2 millimeter wave cells in the same indoor location. The second phase, as I said earlier, is the measurements. Of course, you want to know how your millimeter waves are behaving in an industrial environment. And for that, you need to see, first of all, how is your coverage? On the left here, you see an initial coverage plot that we did. The antenna itself is on the lower right side of the map that you see. And we were then checking how the coverage is. And on the top left corner, you see a couple of areas where we have marked in black color. That is actually where we have absolutely no coverage. The reason is that you will see that in a second when we go through the hall, there's a lot of big machines standing between the antenna and that area. So we just were missing our line of sight, if you want. Performance is also, of course, an important part. Why we want to experiment with millimeter wave. As it was said earlier as well, we have 100 megahertz bandwidth in the mid bands, but for some applications, this is simply not enough, especially in industrial areas where uplink capacity is also high in demand. So we are constantly measuring the different devices, how they behave and what kind of uplink and downlink ratios they can offer us. The table on the right side, you see some measurements that we have done some time ago. It is a kind of running activity. So during the course and the lifetime of the test beds, we will do measurements and share those. Latency, again, just a simple plot here of one measurement that we've done, uplink latency. So one-way latency was measured here with a payload of 100 bytes in the TDD 6 frame, which is the uplink-friendly TDD pattern. And it's probably hard to see here, but I hope you believe me that we achieved something around 2.5 milliseconds of one-way latency, in this case, uplink. Then the third, and I would say also very important activity block is the implementation of use cases. That is actually why we do it. We want to prove what the benefits are of 5G, and in this case, 5G millimeter wave in particular. So we will focus on implementing both a use case that is requiring high uplink, so uplink from the UE to the network for further processing. This would be a machine vision use case. And on the downlink side, we have the typical maybe data shower application that we will also explore what is achievable with millimeter wave deployments we have in the indoor environments. And now I will switch screens here and start filming my colleague Niklas as he walks through the facilities here, and he will then briefly show you our live demo that we have prepared for you.
Should be unmuted now.
I currently don't have a video and I don't hear you, Niklas.
Yeah, one second. We are right back in a second.
Oh, okay. You are aware. Of course, we did test that in advance, but something happened in the meantime. But Bart is working on it.
Okay, we should be back by now.
And no video yet from Bart's device.
Now you should have a video.
Not yet. At least at my end. Oh, Ralph, do you see a video? No.
Unfortunately not.
Okay, then we have another solution. We just take the laptop as camera.
Okay. Sorry for technical difficulties here to the audience. Take the laptop. Okay. Cool.
Den Hintergrund weg. Okay. Vernehmen. Okay, now.
Yeah. It works.
Okay, sorry for the inconvenience. We are now here at the IPT shop floor. Welcome. We presented you already in the presentation this robot. You can hopefully see it right there. This is a multi-technology robot system for adaptive manufacturing. We are able to switch the head of the robot to do different tasks with it. And one task that is now going on, not live, is wire-based laser metal deposition for additive manufacturing. And to monitor this process, basically, infrared cameras are used. And the infrared camera that we are using here has quite high uplink demands, so around 650 megabits per second. And we see on the table there the mmWave UE, which connects the camera to the 5G network via millimeter waves. We now quickly want to just start the camera and show the data transmission. You can follow me do this process. We connect the camera now. Now it's connected, and if we start the video stream, then you can see us here. You can see me from behind here with the camera connected. You see the laptop, which is warmer than I am probably, and yeah, there on this table the connection with the mini PCs and the millimeter wave device was accomplished. Okay, that was our quick millimeter wave demo. Thank you for your attention, and I think we can then open the question and answer session.
Thank you, Niklas. Thank you, Bart, for your presentation. and also for the great time management and for finding a quick solution for the video that didn't work properly. So we had a question in the chat that was directed at Ralph. Again, please feel free to ask questions in the chat or in the Q&A window when it comes up. The first question was about the uplink and downlink data rates that were measured. And just for the audience that doesn't read the chat in the recording, these measurements, just to clarify, they were based on different TDD configuration. That's correct, Ralph, right?
That's correct, yes.
I have a follow-up question for that. If you changed the TDD configuration from more proportions for downlink and to more proportions for uplink, why is the maximum data rate so different? Do you have an explanation for that?
Yes, because in uplink, the devices only support MIMO 2x2 and not MIMO 4x4. So in downlink, you have 4 data streams, while in uplink, you only have 2 data streams, which explains roughly the 50% degradation.
Ah, okay. Thank you for clarifying. Then there's also a clarification in the chat. I guess, Niklas, some logos were mixed up a bit from testbed 11 and from testbed 4. Just for clarification, your testbed that you presented was starting to be endorsed last year. So just to clarify. And then there's a question, Niklas and Bart, to you in the chat. We saw the test results for over 2 gigabits per second for downlink and for uplink 1 gigabit per second. And the question is, how many component carriers are used for millimeter wave and how many layers are used in downlink and uplink in your testbed?
The layers I would need to check. I can leave my contact details in the chat so we can provide that information later on. Component carriers for the uplink depends a bit on what chipsets we use. So I showed the different devices. It's either 2 or 4 component carriers that are being supported by the current devices that we have at hand. So it depends a bit on the chipsets generation. These figures were achieved with 4cc equipment.
And Bart, when you're talking about equipment, what was your experience with millimeter wave equipment, the commercial availability and the usability?
Yeah, as I said briefly in the presentation, bit hard to find equipment. Of course, there is millimeter wave phones available for the US. Unfortunately, the US is using phones and equipment in a different spectrum as we have in Europe. So for industrial devices in Europe with the spectrum that we can get, for instance, from the German regulator, it is barely existing, or any real equipment is not existing. We still are working with the evaluation boards. I think we have some of the colleagues here in the chat. So we have devices from Quectel that you probably saw, Telit, and then we have an so-called MTP mobile test platform from Qualcomm as well.
And this is what you, since there are no further questions right now, I will ask some of my questions.
Sure.
Happy to get some chance to do that, but also please feel free to put questions. You have shown a coverage graph from your facility where we could see close to the millimeter wave radio head. It was a good signal, but then in the other end of the hall, you lost the signal. And you said that was due to a big machinery. Regarding the penetration properties of millimeter wave, do you have any experience with that? Is it like you lose line of sight, then you lose the connection?
Well, if I and you add in maybe Niklas. So for a non-person not involved too much in the physics, actually millimeter wave from the initial measurements that we've done, and we as you saw, we had Rohde and Schwarz, for instance, as a partner, so we will do more detailed measurements, but it's not as bad as we initially expected. So there is reflections, especially in these industrial environments with a lot of metallic surfaces that seem to help in getting some of the beams then bend around the corner if you want. So it's not just direct line of sight that is required. Of course, if you have a lot of equipment in between the position of the UE and the radio head, then of course at one point in time you will lose your connection. But
And
you did know
Niklas,
that.
you want?
Yeah, I can add some things because I was previously involved in an outdoor measurement campaign for millimeter waves. It depends a little bit on how narrow you form the beam. If it's pretty narrow, you could, for example, say also that a human body, a little bit depending on the BMI, attenuates the signal between 15 and 25 dB. So if you want, you can calculate how close you are to your receiver sensitivity, and then you see how sensitive the receiver is to obstacles. So, but as Bart already mentioned, especially in indoor environments, we saw that many reflections appear that are positive for the signal.
And there's a question from the chat that fits perfectly. From your experience, what would you say is a realistic estimation of a distance for millimeter wave?
Yeah, from my feelings, it's a little bit depending on the environment, how dynamic it is. If you have a clear line of sight, you can probably reach distances between 50 and 150 meters. I know that there are papers claiming even higher distances, but I think in this region we would move for the maximum distance.
Thank you. Ralph, a question to you. You pretty much made very clear that Open RAN in the early phase was quite complex to install, to handle, to manage. And in the end, you said that you expect things to be more manageable, especially for end users that are not non-experts with 5G. As of today, what's your impression on how usable Open RAN would be for industrial use cases?
Okay, we have one big German manufacturer that has already announced a commercial industry-grade 5G system. This is going to be launched during this year with first customers. So I would say the technology as such is manageable in the meanwhile, and you can build systems that are industry-grade. You need to spend the time to get the correct management and configuration, MMI on top, so to say. I would say, let's say by end of this year, Open RAN is completely suitable for industry-grade use cases and usage.
Oh. So if people want to start or are interested in Open RAN, it would be a good time to do it now.
Yeah, because if you start now, you will anyway have it by end of the year, not earlier. So
yeah, takes some more time. Maybe another question, Ralph, you mentioned that you up to now don't have neighboring 5G networks, so you didn't need to coordinate with neighbors. But what kind of disturbance would you expect if you had neighbors, and okay, probably how to mitigate these?
Yeah, I mean, this is one of the big unsolved questions that our regulator, the BNetzA, has to address in the next, I would say, years, because the only way to get the interference minimized is to synchronize the networks in time and to use the same TDD slot patterns. Yeah, and I would expect that BNetzA at some point in time, if there are too many complaints about interference at the edge of the network, they will have to come up with some measures and with some proposals that neighboring private campus networks, they have to align and they have to find technical measures to mitigate this interference, to mitigate this disturbance. And as I said, synchronization plus choosing the right slot formats is one of the most practical things to do.
And to the best of your knowledge, have you heard of problems due to interferences?
Not to my knowledge, but this is not.
Yeah, it's just we also are talking and communicating in the community. So I was just interested whether you know of some cases. Now I can probably ask Bart as well. Still see him. I don't see Niklas, but Bart is still there. If you have any experience or know of any interference issues between neighboring networks.
Knowing is, well, we actually did some experiments, and colleagues of ours from Ericsson Research have published a paper on some of the experiments they have done on coexistence and possible interferences. So what I can offer is probably what's I would need to look it up. I don't have it. Cannot give you the link right now, but I can put it in the chat, and then you can read a bit about it. What you sometimes have is the spectrum that's Deutsche Telekom was allocated is just below the campus spectrum we have in Germany. So sometimes you get hints to avoid having disturbances from by changing TDD patterns on the spectrum that's Telecom is using. Sorry, I'm trying to do two things at the same time. Niklas is looking at the sharing the link.
Question. The link, okay. Because there's also a new question in the chat, and then let's take this as the last question for today. Niklas, Bart, what was the millimeter wave transmit power used in the experiment?
We are 10 watts, so we have less issues with the regulator. Of course, this is the output power that the transmitter is giving. The effective radiated power will likely be higher due to the PAM network or the PAM antenna that we're using. But we are not radiating with high power.
Okay. So indeed, no further questions, just the link that Niklas promised in the chat. I'd say we have a perfect time management today in our web seminar. It's 1 minute to the top of the hour. Thank you very much, Ralph. Thank you very much, Niklas and Bart, for your presentation. And also to the audience, thank you very much for taking your time. If you are interested in the other testbed presentations, both recordings should be available by now via 5G-ACIA, and the recording of today's web seminar will be available soon. This is regarding the testbeds, the last web seminar. So we'd like to thank you for joining. Stay tuned for further web seminars of 5G-ACIA. They will be published on the website. And with that, let's close the session. Looking forward to meeting you again, and have a nice afternoon, a nice day. Bye-bye.
Thank you, Lisa.